Howdy folks. In this video I'm going to show you how to make one of these cables and how it can extend the lifespan of the batteries in your rechargeable devices. But before I get into this, I want to talk a little bit about lithium-ion batteries in the first place, about how they degrade and what you can do to increase their longevity. So chances are you have a number of devices which all use rechargeable batteries that are usually built in, and the most common chemistries are, of course, lithium-ion and friends. And as we all know, these batteries don't last forever. They have a lifespan, and eventually, they degrade to the point where you have to essentially replace the battery. And with the current state of affairs with devices, replacing the battery is usually not an easy task, even if you can even get the battery in the first place. So obviously, you should support right to repair, and we should be forcing manufacturers to allow us to repair our devices. If you want more information, look up Louis Rossmann or something, and they'll explain it. But anyway, until sort of that stuff happens, you obviously paid for your device and the battery, and you want to make that last as long as possible. At least I do. And so there are a few things that you can try to do which can improve the lifespan of the battery. When I say lifespan, I mean how many years it has a reasonable capacity for. So the first thing to note is that lithium batteries do not like to be fully charged, and they don't like to be fully discharged. If we're anthropomorphizing, they basically just don't want to exist at all. But since that's not really an option, they would prefer to be about 50% charged. So it's sort of commonly accepted that if you use it between 80% and 30% state of charge, that is sort of the easiest range on the battery. Now, of course, that only gives you 50% of the battery's capacity, but I would argue that a lot of people don't need more than that on a regular basis. Obviously, you can charge it all the way and discharge it all the way if you need that capacity, but most people probably don't need that capacity all day, every day. And so keeping it within that range reduces the stress on the battery. Now, as far as not discharging it below 30%, well, that's entirely on you. Basically, if you're one of those people who waits until the battery gets to 3% before you bother to plug it in, well, you're murdering your battery, and you need to fix that. As far as not charging it all the way, though, it's not terribly convenient on a lot of devices, and since most people charge their devices overnight, it doesn't really make a lot of sense to have to get up and unplug it. It's just not viable. Some devices have settings or the ability to stop charging at 80% or whatever. So, for example, I have a phone. This is a Sony Xperia 1 III. This has the ability to do that. You can tell it to cut off at 80%. Some laptops allow you to do the same thing, and that's great. And you should support manufacturers that add those options in. If you don't have that, sometimes you can you can root your phone. You can put custom software on it that'll allow you to do that. Your options are going to be determined by what hardware you have as far as the upper limit of charge. But if nothing else, just avoid using the lower, avoid doing a deep discharge if at all possible. Now, sort of related to that is depth of discharge. And so depth of discharge is just simply how much of the battery capacity you use from full before you charge the battery up again. And you want to reduce the depth of discharge as much as possible. And the reason for that is because the ratio between depth of discharge and number of cycles the battery can endure is non-linear. So what that means is if I had a battery that was 100% charged and I completely discharged it to 0% and charged it back up again, so that would be a 100% depth of discharge, right? 100 minus 0 is 100. I would have pulled that capacity out of the battery. Now, if I took the same battery and I had it fully charged, I discharged it 50% of the way to 50% state of charge, and then charged it back up again, and then I did that twice, so I had two 50% depth of discharges, and so 50 plus 50 is 100. I've still got the same amount of energy I've pulled out of that battery. I just did it in two cycles. If these are just some theoretical numbers here, but let's say that the battery is rated for 400 full discharge cycles, but it may be rated for like 1,200 50% discharge cycles. So, 1,200 is more than 2 times 400. So because of this like nonlinear relation, the shallower the depth of discharge you do, the more cycles of that depth you can do in a nonlinear relation. So basically, charging more frequently rather than doing a deep discharge will extend the life of the battery. The next thing that you want to try to avoid is excess heat. So lithium batteries, they don't like to be hot. So I wouldn't recommend keeping your devices in the sun or in a hot car or anything like that. Try to reduce the heat while they're in storage and while they're in use. Now, obviously, if you've got a phone with a powerful processor and you're gaming on it or whatever, the phone itself is going to get hot and it's going to heat the battery, and there's not really a whole lot you can do about that. But if there's any incidental heating, you can try to reduce that. And the last thing I want to talk about is the charge and discharge rates of the battery. So the C rating, that also affects the battery lifespan. So the more current you the more current that you use to charge or discharge the battery, the more degradation occurs. And part of this is chemical, and part of this is thermal. So related to the last one, if you've got a lot of current due to the internal resistance of the battery, it will self-heat under charge or discharge, and of course that's bad. But even if you were to keep the battery cool somehow, you still have chemical degradation. So ultimately, you want to reduce the speed at which you charge or discharge your device. Now, what's interesting about charge rate is that the industry trend is towards higher and higher rates of charge, which is going in the opposite direction of what you want for battery longevity. So originally, we started with USB charging, which was up to 500 milliamps with enumeration, and then we moved on to fast charging standards, where we were pulling, like 2 amps or something through at 5 volts, and then we had proprietary standards like Qualcomm Quick Charge, where we increased the voltage, and then we had with USB-C, we've got of course USB power delivery specs. And we've got chargers that are now 30 watts, 60 watts. I think that there's like a phone that can do 100-watt charging, something ridiculous like that. And so these are all things that like this is the charger that came with my phone, and it is rated for 30 watts. And the thing is, if you use this charger, it will always charge at 30 watts. There is no way to tell it to charge slower. And so since myself and probably a lot of you charge your devices overnight, there is no need to charge it at 30 watts. You're just needlessly doing damage to your battery. And sometimes, and of course, one thing you can do is you could just get a charger that is not not new. Get an old charger that can do maybe like 1 amp or something, and plug it into that. And that is an option if you have one of those chargers, but there are some disadvantages of that. One of them, of course, is if you're traveling or something and you want to bring a fast charger just in case. Well, now you have to bring 2 chargers, a fast charger and like a slower charger. And of course, these things they're not insignificantly tiny. Or you may be in a situation where you've got a power bank or something like this, which again is also quick charge capable. And this kind of thing, again, you can't turn it off. And it's like, well, I don't want to buy a shitty power bank that doesn't have quick charge capability. In fact, almost all of the good ones do have it. And again, you can't turn it off. So you're kind of forced to use something like this. So this is where this comes in. And so I designed this, and I'm probably not the first person to design one of these, but I actually looked for something commercial that I could buy that did this, and I wasn't able to find anything. And so this is introducing the revolutionary slow charge cable. So this is just an Amazon USB-C to A cable that I bought that I cut in half, and there's some special sauce in this box which allows you to adjust the charge rate through this cable all the way down to 150 milliamps. So you can go from 1.5 amps all the way down to 150 milliamps with a little dial in here, and that allows you to set the charge rate. And so what I did was I can take, I can sort of by experimentation, I found the exact charge rate that I needed so that my phone would charge from 30% to 80% in 8 hours, which is, how long, I try to sleep for. So that way it charges as slow as possible, but still gives me the full charge I need in the morning. And you can build one of these for not a lot of money. You just need a bit of soldering skills, and that's it. So let's take this apart, and I'll show you what it is. I'll give you a schematic, explain how it works, and yeah, it should be compatible with pretty much all devices that support charging at slower speeds. So it's it's pretty cool. Obviously, this box is mostly empty, so if you wanted to make it smaller, by all means you can. This is just the size of the box that I got on Amazon. So I know I'm saying about size, and I'm saying, yeah, obviously this is pretty big too, but it's not, doesn't have to be this big. It's just because this is what I had. This is what's inside that box. As you can see, it's a little PCB. I've got some knots tied in the cable to prevent you from pulling it out of the box, and of course putting strain on the solder joints here. When I make this more permanent, I'm gonna glue it in and everything. But anyway, it's a little piece of just perf board, and I've chosen everything is surface mount devices except for the pot here. Obviously, I could have gotten a surface mount pot if I wanted, but I think really to make that make sense and to make this as small as I'd like it to be, I would get one of those PCB prototyping houses to make a custom board, because of course this board is tiny, and so you can get really cheap boards, and you get them in large quantities. Like quantities of 10 for like $5 or something like that. So that would be the ideal way to do this if you wanted to make a bunch of these cables. And obviously, the more cables you make, the lower the cost per cable because of a lot of the stuff you have to buy. So it makes sense to make a couple of these, and that way you could have different currents and stuff. And I have a couple other designs as well. There's ones that include bypassing switches and things like that. So anyway, basically, I just bought a cable. I bought an A to C cable specifically because the A to C cables only have 4 conductors. If you want to buy a C to C cable, it's a little bit more complicated because C to C has additional conductors for doing the things like USB power delivery negotiation and stuff like that. So I recommend for doing your first cable, I would recommend you just do the A to C or the A to micro B or whatever, because it's only got the 4 wires and it makes things a little bit more straightforward. So on the input end, so this is the end that has the USB A on it. Basically, it's just got power coming into the board, and the 2 data wires are just lopped off. They don't go anywhere. On the output side, the data wires are soldered together, and I didn't have any heat shrink, so I just put some electrical tape. So they're just shorted together. And when you short them together like that and you leave them floating, that is part of the battery charger standard that just tells the device it's connected to a device it can't enumerate with, because of course there's just power coming in, there's no actual data. And that's important to have. Everything else is done on the board here. And so the heart of this is a really tiny little 5-pin chip here, and I've just got some ceramic capacitors on the input and the output, and then I've got this little trimmer pot here, and it's all very sort of ghetto soldered together, but of course this is what a prototype looks like. The schematic for this circuit is incredibly simple, and of course it's all based around a single chip, and you don't have to use the exact chip that I chose, which is from onsemi, because there's an entire class of chips that do this function. They're basically just power switch ICs. As long as they have certain additional features, it'll work just fine, and I'll explain that in a moment. But the chip that I picked, like I said, is from onsemi. It is the FPF 2125, and in Canadian dollars, these are about $1.75 in one quantity, and of course you buy them in multiple quantity, and they come in these little 5-pin packages. And of course this looks very small, and that can be very daunting to someone who hasn't soldered before, but I used pad per hole through hole board, and you can use these with that because the pin in the middle on this side is the only one that doesn't line up. So all you got to do is just bend that pin up, and then just solder a wire to it to a nearby pad, and the other 4 corners can go into they can just solder onto the pads. So it is possible to solder these onto those pad per hole boards if you want. You don't need SMD boards, or you can get little SMT to like dip adapters off eBay or whatever. If you want to do it that way, that also works. But of course, those are going to increase the size of your little blob in the middle of your cable. And so this chip, it has an in and an out. So the in is obviously the power that comes in from your charger, and the out is obviously the power that goes out to your device that you're charging. It's going to need some decoupling. So the datasheet recommends a 4.7 microfarad on the input, and they recommend a 0.1 on the output. I didn't use 0.1. I didn't have that, so I put a couple other caps together, and I think it's only like 0.2 or something, but it's not super critical on the output side. And I used MLCCs, they're surface mount, of course, because they're small, and that's what I had. But of course, you can use larger stuff if you want. The chip has a ground pin, obviously. It's pretty straightforward. And then it has this sort of this on pin, because of course this is a switch. So the idea is that you would have like a microcontroller that sends a signal to this pin, and there's a built-in FET inside the chip that turns the output on, so it connects these two together. And so we're not going to be using that functionality because obviously we don't want the cable to turn off. We want the cable to be on all the time. So we can just tie this directly to the input so that it's on all the time. This particular chip is a logic high on state. You can also buy chips that are logic low, in which case you would tie it to ground in that case. And so far it's just a switch. Nothing is fancy here. But what is important is the fifth pin, and this is an iSense. So this is a current sense sort of pin, or it's really not a sense. I shouldn't say that. It's sort of an iSet. It's a current set pin. And so what you do is you place a resistor between this pin and ground, and this resistance is what sets a current limit through this device. So it can act as a constant current source based on this resistor. And so the specifics of how this works are going to be dependent on the exact part you choose. So the FPF 2125 is part of a family. There's also the 2.4 and the 2.3, and the 2.3 is the most commonly sold. It's actually much cheaper, but you probably don't want the 2.3. You definitely don't want the 2.4, and the 2.5 is actually the most ideal for this application. And so the minor details in how this work are really the secret sauce in this whole thing. So anyway, just for completeness, I used a variable resistor, or in this case I used a pot. So you just tie this to the wiper, and that way I can just adjust exactly the current that I want. If you want, obviously you could put a fixed resistor in here. That would make it much smaller and all that other stuff. But I find this is the most convenient, because not only can you trim it and set it to what you want, because different devices are going to behave differently a little bit. Some devices you can adjust them to very precise currents. Other devices, they only work in 100 milliamp or 250 milliamp steps. The charge circuitry in your device that you're charging is going to determine how well this works. And then the other thing is the precision of the reference inside these is not very good. So the datasheet has a very wide range of currents for a specific resistance, and so you can trim out that tolerance with a variable resistor. So I recommend the variable resistor option. But anyway, back to how this works. It's pretty straightforward. The device obviously is going to try and pull current, and when you reach the current limit, this device is the voltage, of course, on the output is going to drop. And so most devices, when they see a battery charger, they just start to pull more and more and more current until they see the voltage start to go down. And once the voltage starts to go down, they sort of back off a bit, and that's the current that they charge at. And so by setting this current limit, this will let that amount of current through before it goes constant current, and the voltage starts to go down, at which point the device will back off. And so it doesn't matter how much current the source can supply, the output can only supply however much current you program into this device. Now, in the case of the on-semi parts, this last digit is important because of how the overcurrent condition is handled. So on the 2125, the device will supply the rated current indefinitely as long as the chip doesn't overheat. And that's perfect because the device is just going to pull too much current, it's going to go constant current, it's going to back off, and it's going to be fine. The device isn't going to get hot, it's not going to dissipate much power, it's really perfectly fine. But the device never shuts the output off during this, which is exactly what you would expect a normal power supply to do when you reach the maximum output power. Now the 2123, actually once the output current limit is exceeded, it shuts the output off, and then 10 milliseconds later it turns it back on again. So it has this self-reset behavior. Now that might work, but it's up to the device you're charging. Some devices, like I have a power bank, that absolutely would work fine with that. If it quickly sees the output or the input go away and then come back, it says, oh, I pulled too much current and I caused it to overcurrent, so I'll back off. In which case the 2123 will work just fine. Other devices, they may not figure that out, and they may just keep retrying the same current over and over and over again and not get anywhere. So the 2123 might work, might not. I haven't tried it yet. The 2124 you definitely don't want because that's the one that latches. So as soon as the overcurrent happens, it latches and you have to reset the chip in order for the output to turn back on again. So obviously that's not going to work in this application because we expect the overcurrent condition to happen. So anyway, this is the chip that I chose, but you can get chips from a bunch of other vendors. You just have to check the data sheet for exactly how their current limiting behavior works and how the reset behavior works. A lot of the chips don't have current limiting, so obviously you can need one of them with those. Something that has a way that you can enable it all the time, whether that be active low or active high. And you also want to make sure, of course, that the voltage tolerance on them, of course, this chip is not specific to USB. It doesn't say anywhere on the datasheet that it is specifically for USB. Some of them are, some of them aren't. This one can do 6 volts, absolute maximum, and it can also tolerate 6 volts on the on pin, which is important because that way we can just tie it directly here. Some of them can only handle logic level on this pin, and so you'll need to use a resistor divider if you choose one of those chips. So that's really it. It's not very expensive. Obviously, these capacitors are just a couple cents. The chip, like I said, is going to be maybe $1.50 to $2 Canadian pesos if you buy it in single quantity. The pot's probably going to be about 50 cents or so if you buy, again, one quantity. And then the board and the case, obviously you can get a case like this. I got, I think, 5 or something of these cases for $10, something like that, off Amazon, like Prime. So obviously I overpaid for these because I wanted them sooner, but this is pretty big for the size of the board, so you don't have to obviously get this case. You could just heat shrink this. That would work perfectly fine, and then just sort of poke a hole for the pot in there. That would work totally fine as well. There's many different packaging solutions you could do. This is very much a sort of a first prototype. So I might as well show this working and how I actually calibrate these. And to do that, I'll bring in a sort of a power bank that I've got. This is a just like one of those Anker power banks, and this thing outputs 2 amps, so it can do 2 amps on these ports. And then one thing that makes this process really easy is to have one of these like USB current meter things. You can use a multimeter, obviously. You can just tap into the pins and check the current there, but this just makes it a little bit more convenient. I don't recommend ever buying this as a terrible one, but it does give you the current to at least some precision, so that's good enough. This power meter or this power bank has a current in it as well. Again, lower precision, but it'll work as well as long as you can figure out what the current is, so that you can adjust this correctly. That's the real thing that you need. Okay, so I found a regular cable that I got in the same pack. It's exactly the same cable, but I didn't cut this one in half, and I'm going to plug in my phone, which is the Sony Xperia 1 III, like I previously stated. So we're just going to plug this phone in here, and we're going to watch the current, and you can see it's at 1.43 amps is what the phone is charging at, and it is charging. Okay, so the phone fast charges on this device, which of course we don't want it to do. So we're going to replace this cable with the modified cable, and of course the cable, even though it has active circuitry in it, it doesn't draw enough current to keep these power banks active. So you can see this power bank is already shut off, and this is running off the output capacitance. So this will turn off if I don't turn it back on. So you don't have to worry about leaving these cables plugged in or anything. They're not gonna cause any problems with current draw or whatever. And I have to find the output because this cable is super long. So what we'll do is we've got the same phone here, and we will plug it in here, and you can now see that the phone is still charging, but you can see now it's only charging at 330 milliamps. And so this is the current that I dialed in. I originally had it down to 210 milliamps, but which would have charged it perfectly fine in the 8-hour period. But I also use like sleep monitoring. I have one of those apps, monitors motion and stuff, and that draws enough extra current that it wouldn't actually charge fast enough. It was actually too slow, so I had to bump it up to 330 milliamps. And so having this allows you to easily check it to set it. So the way I did it was I just sort of unplugged it. I would then get a little screwdriver, tweak the pot, and then I would plug it back in and see what the device tried to charge at. And I would just keep doing that until I got the current that I wanted. I don't recommend tweaking the pot while it's on because I don't think the device is going to try to continually draw more current. I think the device is just likely going to figure out what the max is and stay there. So I wouldn't recommend doing it while it's plugged in. You're probably not going to have a good time with that. So yeah, that's the basics of it. It's very straightforward. Yeah, it's easy, it's cheap to build, all you need is some soldering, and this can extend the lifespan of your battery. And I know that some people are going to say, well, just enjoy life, just use the product as designed, and that's totally fine. No one's forcing you to buy this, but of course, I consider these kinds of devices an investment, and I want my investment to last as long as possible. And so, a little cable that I can build for a couple dollars that can, save maybe, I don't know how long it'll actually make a difference for, a year or something. I don't know. Only time will tell. But I think it's a neat thing to have. So yeah, I hope somebody tries this out, and I hope someone finds this useful. And until next time, thanks for watching.